So, good afternoon, everyone. I'm Gitanjali Jaina. I'm a PMRF scholar from IIT Delhi. So, I welcome you all to the first live section of this course, Introduction to Laser. So, in this course, we will discuss about the concept that is discussed in the weekly course, as well as we will solve the problems that will be related to the concept. And these problems will help you to understand the concept better, as well as this will help you to solve the weekly assignment that will be posted in the forum. So before starting the section, I'm happy to tell you that Professor Ahmad Senoy sir is also with us. So sir, could you please talk with the student for a few times? Hello. Yes, sir, I have unmuted you. Oh, okay, sir. Give me a few minutes. Okay, sir. Sir, you are unmuted now. Presented. Is is it fine now? Okay. Okay.
Yes. Okay, yeah, I'm there. Hello, good afternoon, everyone. I hope you are able to hear me. Anjali, maybe unless you unmute them, they will not be able to respond.
Yes, sir. I have unmuted
Yeah,
all.
all is it?
Sorry, I'm muted all. All are muted
So,
actually.
but now you can unmute because it is more like an interactive session. Otherwise, and
Okay.
when you start your presentation, then you can mute again.
Okay. Okay, let me unmute.
Yeah,
Uh,
unmute all if you make.
oh, yes, sir. All are unmuted now.
All are unmuted. Yeah.
Yes.
So individually, each one of you can unmute yourself. Now you have permission to unmute. Anjali, please check whether you can unmute yourself or not.
Yes, sir.
Yeah, you have unmuted. Correct. So everyone can unmute yourself. Hello, Sangamitra, you have unmuted. You can hear me?
Yes, sir.
Okay. I just wanted to get a response whether you are able to hear me or not.
Yes,
You
sir.
can
I can
hear?
hear. Yes,
Okay.
sir.
Okay. So should we wait for a few more minutes or can we start? Anjali, do we start or not Anjali, Gitanjali? Shall we start then?
Yes, sir, we can start now. It's
Okay.
already 5 minutes. So we
Yeah.
can start this.
Okay, so some of you, good afternoon to everyone. And some of you may have already done some NPTEL courses. And though some of you may be new. So as you know, we want to keep every week one discussion session, so that if you want to discuss something, then in person you can discuss with the PMRF TA. So Gitanjali is doing PhD here in IIT Delhi, and she's also a PMRF fellow. So this is one-to-one discussion which you can have. And the second one is, of course, there is a forum where you can ask questions. And there are two of our senior PhD students who will be responding to your queries. If you have any query, any technical query, anything on the subject, you can also raise there. So I think they have joined. Anjali is here. Maybe I will spotlight for everyone myself so you can see, right? Yeah. So Anjali is there, and also there is Kaur. So both are senior PhD students. They are about to complete their PhDs. So they would respond to you in the forum. And if you have any question, you can raise that. But also you can discuss with Gitanjali. Every week she is giving a discussion session and a presentation. So this time what we have planned is, what I have told her is that if you would go through, that is you as registered students, if you would go through all the videos, then at the end of the week, that is every Saturday, she will discuss about the 3 video lectures which you were supposed to go through. She will discuss on slide. You are also provided the slides, these handouts. These slides, hello Gitanjali, these slides are also available to them, no, for downloading.
So, sir, it's not uploaded till now. Some of them have asked the query in the forum.
Is
So
it?
maybe yes, sir. Only the videos are, I think, available, not the PDF file of the slide.
Oh, then probably we should also upload that. I think earlier we had given, because that will be, as you know, very helpful to them, because they can also make some notes on the slides itself. They can probably take a printout and make a notes right on that. Then that will be very helpful to them.
Yes, sir.
So what Gitanjali will do is she will go through the slides which I have presented lectures, and any specific slide or any specific aspect which is not clear to you, even after going through the video lecture, you can ask her so that she will clarify what it means. And in addition, if time permits, she will also work out some problems. Some new problems also she would work out. And also, once your assignments are over, as you know that at the end of the week, then it will be evaluated, and your score will be uploaded. So once the evaluation is over, if you have some doubts, then you can also request her to discuss about the assignments which you have already done. Maybe you made a mistake, or maybe you did not understand. And such questions also she would discuss. In addition, she may discuss additional similar problems. Okay, so that is the plan. And in the earlier years, we did not have the discussion forums where the students discussed on their own some additional materials. And many times the students lost interest on those additional materials. That is why instead of discussing only the additional material, what Gitanjali will do is revise the three lectures of the week which you have gone through on slides. So that any place, if you want to have a one-to-one discussion, then you can do it with her. This, I think, will be very helpful to convey. And the second point which I wanted to convey is that the course is really very easy, provided you are very regular, because all the type of questions that you will get, including in the assignments, will be testing your understanding, a thorough understanding. So you will see that even though the questions, many of the questions are of MCQ types, it will really test your understanding, and the emphasis is on understanding. In the final exam also, the questions will be similar to what you will be doing in the assignment. And wherever there are numerical problems, here in the assignment, there will be some numerical problems, but we will not really give you formula in the assignment. But in the final exam, wherever a formula is required, that formula will be given in the question itself. Therefore, you don't need to mug up any formulae. The formulae will be given to you. And therefore, it will be primarily testing your understanding. So what is required to do well in the course is really a continuous revision and a serious follow-up. So please go through the video lectures completely, including the many things which I write by hand over the slide. As you see that it is annotated with my handwriting as I discussed on the video lectures. And the additional discussion which I made by hand, written by hand, is also very important, as you will see in doing the assignments. So this is what I wanted to convey. And I plan to join the discussion system as and when possible. But Gitanjali will make presentation every week, so that you have two forums now. One discussion forum where you can put a question and anyone can try to answer. Or alternatively, you can also discuss with in person, online of course, in person with the Gitanjali face to face. So if there is anything that you would like to ask, please feel free to ask. And you can unmute yourself, because she has unmuted all of you. And you can specifically unmute yourself if you have any particular question. Or you can raise your hand also. So if you raise your hand, then that is also possible. It could be about the subject or about the exams or whatever, if you have any. The background that we assume is at an undergraduate level. So it's not because it's an introductory course, and therefore it is at the level of undergraduation or a first year MSc kind of a course, first semester. So therefore the level is not high. There are very little quantum mechanical and quantum field theory involved, primarily classical approach to a quantum electronic device in its simplest possible form. Gitanjali, is there anything you would want me to talk, or any participants, if you have any question? Otherwise, I will hand over to Gitanjali and she will start discussion. We will try to upload this. The PDFs apparently are not available to you right now. And we will definitely upload those PDFs because that will be really, we know that it will be very helpful in when you prepare for the exams and so on.
So anyone has any query to ask to Vinod sir?
Mamta, I am very much here. Why don't you unmute and ask? Feel free to ask. No question is silly question. So please feel free to ask whatever you have. Because I am live here, no? Instead of my typing answer to you, you can unmute. And are you not able to unmute? Let me see.
Oh, sorry. Yes.
Yeah, you are. Yes, you are able to unmute. Why don't you ask if you have any query?
I have a doubt regarding laser comparing when laser is compared to an electronic oscillator.
Uh-huh.
I mean, why only
Yes,
electronic oscillator? I'm not
yes, yes.
able to connect the comparison. मतलब इलेक्ट्रॉनिक ऑसिलेटर क्या है और उसके साथ ही कंपैरिजन क्यों, या मतलब ऐसा कुछ कोई ऐसी इंफॉर्मेशन जिससे ज्यादा मुझे कुछ समझे इसके बारे में.
ये कंपैरिजन जो है, तो दिस इज बिकॉज व्हाट इज एन इलेक्ट्रॉनिक ऑसिलेटर? इलेक्ट्रॉनिक ऑसिलेटर इज ए सोर्स ऑफ रेडियो फ्रीक्वेंसी, है ना. आपके पास एक ऑसिलेटर है, तो समझ लीजिए आपको 1 किलोहर्ट्ज का वेव चाहिए, 10 किलोहर्ट्ज का चाहिए, स्क्वायर चाहिए, साइन चाहिए, जो भी चाहिए. सो दैट इज एन ऑसिलेटर विच इज ए सोर्स. इट्स ए सोर्स. उसके आउटपुट में जो आता है, दैट्स एन इलेक्ट्रोमैग्नेटिक वेव इन द रेडियो फ्रीक्वेंसी. Is that correct? So in that sense,
Yes.
A laser is a source of electromagnetic wave, exactly like an oscillator, but at the optical frequency. So first comparison तो यही है, क्योंकि दोनों सोर्स है, सोर्स ऑफ इलेक्ट्रोमैग्नेटिक रेडिएशन. पहला वाला रेडियो फ्रीक्वेंसी रेंज में है और दूसरा वाला ऑप्टिकल फ्रीक्वेंसी रेंज में है. अदरवाइज दोनों सोर्स ऑफ इलेक्ट्रोमैग्नेटिक रेडिएशन. फर्स्ट पॉइंट. सेकेंड पॉइंट तो ये है, दोनों का कंस्ट्रक्शन में क्या है. तो इलेक्ट्रॉनिक ऑसिलेटर का कंस्ट्रक्शन है, एक एम्पलीफायर डिवाइस होता है और उसमें एक फीडबैक सर्किट होता है. कोई भी इलेक्ट्रॉनिक ऑसिलेटर आप ले लो, उसमें एक एम्पलीफायर और एक फीडबैक मैकेनिज्म और फीडबैक सर्किट होता है. तो उसी तरह लेजर जो है वो भी एक ऑसिलेटर है, होगा और एक फीडबैक मैकेनिज्म होगा. तो वो आप जैसे आगे पढ़ते जाएंगी, यू विल सी दैट फर्स्ट लेजर एम्पलीफायर विल बी डिस्कस्ड. उसके बाद हम जब उसको मिरर लगाएंगे दोनों तरफ से, द मिरर फीडबैक देगा. फीडबैक मतलब ए पार्ट ऑफ द लाइट विल बी रिफ्लेक्टेड बैक इनटू द मीडियम विच इज फीडबैक. तो इस पॉइंट ऑफ व्यू से भी वो दोनों कंपैरेबल है, दोनों सिमिलर है in performance. You will see that the performance will also be similar as you discuss further. Is that okay? Mamta, is that clear?
Yes sir. Means दोनों भी waves input देते, मतलब नहीं,
दोनों में इनपुट
sorry,
नहीं
wave
होता है. दोनों में, हाँ, दोनों में सिर्फ पावर होता है. मतलब पावर सप्लाई होता है. एक ऑसिलेटर को भी आप पावर सप्लाई देते हैं, है ना. वो एम्पलीफायर ऑन करने के लिए पावर सप्लाई तो चाहिए. अगर आप ऑप एम्प यूज कर रही है तो उसके लिए +-12 सप्लाई तो देंगी.
Yes sir.
Is there any other question? So about, of course, the subject as such, Gitanjali will discuss any question that you have. So you will be free to discuss any doubt in these 3 videos, because she will go through those. She will show you all the slides which I have used in the video lecture. So किसी भी point पे आप you can stop her and then you can tell her that madam, in this slide we did not understand this, what sir has said. So always feel free so that it will become interactive. It should not become one way. So that's why you can unmute yourself, ask your question, discuss, interact, and then you can continue. Otherwise, if it is just one way, you will soon lose interest. Therefore, it is very important that you interact. Is that all right? So if there are no further questions, then I will again join some other time, and I will hand over to Gitanjali. You just see how it goes. We can also
Okay, sir.
discuss. Yeah, you please feel free to ask your questions in the forum. So there are two other senior PhD students, Anjali and Sukhvinder Kaur. Okay. So all these people have done the laser course, so they know about it. So they will be able to help you or clear your doubts. And even if there is something which is beyond that, you can raise in the forum, and they normally check with me whether before answering you, they will answer, or if they have any doubt, they will check with me and get back to you. Okay. So with that, I will take leave, and hope you will enjoy the course. And about the exam, we can discuss some other time. As you know that there is 75% weightage for the exam and 25% for the assignments. Usually assignments are home assignments. Therefore, usually students tend to score almost 100% in the assignment. And that means you already have got 20 to 25 marks. And therefore, from the exam, you need very little to just pass. What I'm saying is just pass. But don't target to just pass. Try to learn the subject and enjoy the subject and try to excel. So passing is very easy if you just put enough work. But here, try to excel in the subject. And as far as we are concerned, we cannot bring down the level below IIT standards, because it's an NPTEL course supposed to be taught by IIT professors. So we have to keep it at the same standard, because as you know, in several technical institutions, including IITs, students can credit these courses up to 6 credits, that is up to 2 courses. They can earn credit from this NPTEL course, and that will be added into their final degree. And therefore, we cannot make it walk over. So therefore, it is very important that you study, because if you see the previous year's performance, the pass percentage is very low. That is because people think that it is online course, you just pass through. It will not, unless you put in hard work and work sincerely. As I said again, passing is very easy, but even then, the pass percentage, if you have seen in the NPTEL website for this course, is not very good. It's not because the course was tough. It is simply because the students took it lightly. So please go through it, and we can discuss whenever you have any difficulty or anything, doubt that comes to your mind. Okay. So I will then sign off. Gitanjali, you can take over.
Okay,
So I
sir.
will.
Thank you, sir.
Okay.
So let us start the section. Please wait for a few minutes. So I think my screen is visible to everyone. Okay. So let us start the section. So based on the concept that is taught in the course, I have prepared some notes based on what Professor M.R. Sinha has taught in week 1. So let us go through it one by one. So started with laser. So laser is it's a acronym used for light amplification by stimulated emission of radiation. So it's a source of optical radiation. So by optical radiation, we mean the radiation which have wavelength around 0.2 micrometer to 20 micrometer. So for visible wavelength, we know the wavelength falls around 0.4 to 0.8 micrometer. But the optical radiation, it covers a wider range than the visible wavelength. So, so for optical radiation, we take wavelength around 0.2 micrometer to 20 micrometer. So if you take an example, such as if you take helium neon laser that we widely use in experiment, so it has wavelength around 0.633 micrometer. And for a carbon dioxide laser, the wavelength is around 10.6 micrometer. So if we now compare this laser source with the source, other kind of sources that is used in other experiment, we found that this laser source has some special properties. So the special properties like the laser source is highly monochromatic, which is quantified by the monochromaticity and line weights of the source, and it is highly directional, which is quantified by divergence angle, and it is highly intense, where we see that the energy of this laser is mostly concentrated around the small cross section of the beam, and the laser is also highly coherent, where we quantify this property by coherence time TC or coherence length LC. So we'll see the details of these properties in our upcoming section. For now, let's see what this highly monochromatic means for a laser. So monochromatic, it means single color or single wavelength. So a source is highly monochromatic. When we say this, we assume that the source is emitting a single wavelength or a single frequency or a single color. But in practice, we don't have any source that radiates a single wavelength or single frequency. So whatever sources we have, these sources has finite spreading around the wavelength at which they are emitting the radiation. So let us understand these properties by taking a intensity profile of a source. So if you see figure 1, so figure 1 is it's indicating a spectrum of a source. The y-axis is it is showing the variation of intensity of the emitted radiation as a function of wavelength. So let's say we have a source and it is emitting some radiation. And in this figure, we plotted how this intensity of light is varying as a function of wavelength. So if you see figure 1, you notice that the intensity is high around the wavelength lambda p. So lambda p means peak wavelength around which we are getting higher intense light. So the intensity is high around lambda p, and in addition to that lambda p, we notice that the source is also emitting radiation that is other than this lambda p. So we see a finite spreading of light around this peak wavelength lambda p. So this is what we mean by that is source is finite spreading. So not every so its source do not emit radiation at single wavelength or single color. So to quantify the monochromaticity of this kind of source, which has intensity profile like this, what we do, we define a term which is line width. So line width is nothing but the full width at half maximum of the intensity. So if you see intensity profile like this, it is the intensity profile of a source. Here, if you take the full width half maximum of this source, which is indicated by this red line, if you see this region. So this is the line width of the source. So by calculating this line width, you can measure the monochromatic city of a source. So if we have different sources which has different line width, then by checking which source is narrow line width, then we can confirm that this source is high monochromatic source. So if we have laser, LED, or other kind of sources, we have to compare the delta lambda of each source to find out what is the monochromaticity of the source. So this is what we mean by monochromaticity. So let us see some of the examples of these sources. Like the first is the tungsten halogen lamp, which we use in day-to-day life. So if you see figure 2, here the figure 2 shows the spectrum of the tungsten halogen lamp. So it is a plot between the intensity of the emitted radiation versus the wavelength of the emitted radiation. So here we see, you can see the tungsten halogen lamp is emitting around the wavelength 0.2 micrometer to 2 micrometer. So for this spectrum, if you want to get a blue color out of this white spectrum, what we usually do, we use color filter. Like if you want to get blue color, you use blue color filter. If you want to get red color, you use red color filter, or green. For green, we use green color filter. So this color filter have line width which is around 50 nanometer. Okay. So now if you use, let's say you want to filter out blue color. So you use a blue color filter. So what it will do, it will filter out shaded region. So if you see the red color shaded region, so it will filter out those frequency which is delta lambda around 50 nanometer around the blue color wavelength, which is 0.4 micrometer. And other than this color filter, we also have interference filter, which is narrower line width than this color filter. So for interference filter, the delta lambda is 2 to 10 nanometer. And the LED that we are using, this has delta lambda, which is 30 to 50 nanometer. And other kind of sources that we also use in experiment, such as if some of you, Mamta, okay, you are unmuted, I think. So please ask your query.
I want to ask that the figure behind the graph you have showed earlier. Yes, this.
Figure 1.
Yes. Figure 2.
Figure 2. Okay.
ब्लू फिल्टर वाला, तो उसमें
Yes.
450 सर ने वीडियो में कहा था कि 450 नैनोमीटर इसका वेवलेंथ है, बराबर, प्लस माइनस 25
Blue
नैनोमीटर.
color. Around blue color, it is wavelength is around 450 nanometer.
हाँ, तो मतलब अगर रेड शेडेड पार्ट को हम कंसीडर करें तो उसके बीच में, एग्जैक्ट बीच में 450 आएगा, उसके पीछे आएगा 425, 475, ऐसा ही ना?
Yes.
ओके, तो ये
So
पूरे
lambda p
पूरे
is
फिल्टर का जो विड्थ है वो है 50 नैनोमीटर, मतलब पीछे 25 आगे 25, तो टोटल 50 नैनोमीटर
50
एवरेज ऐसा.
nanometer.
ओके.
So for this, you take lambda p. Let's say for blue color, it is 450 nanometer, and delta lambda is 50 nanometer. So what you will get in the output is the lambda will varies from 450 plus or minus 25 nanometer. So in addition to blue, you also get some other wavelength which is in the line width around 50 nanometer. So I think it is clear to you, Mamta.
Yes, it's clear. But I have another doubt.
Yes,
Line width, which is full wave half full width at
full
half
width.
maximum, is a measurement of monochromaticity. So
Yes,
ऐसे half full width at half maximum ना, तो half
yes,
maximum के
yes.
लिए क्यों लेते हैं? काफी सारे
It's
widths है.
like, but that intensity is smaller than 50%. Like if you're considering a 20%, it is actually negligible. The intensities are actually negligible. If it is higher than 50%, then you will see the contribution of this wavelength is higher than the wavelength that is at 20%. So that's why we take a margin of 50%. So in this range, we will see the color.
Okay, in terms of
It's
average, we can say
like
average.
20% is much less. It's like that. If 20% of light is there, then it is almost negligible. So that's why we take a margin of 50% and we tell ki line width is full width at half maximum. It falls within this range.
Yeah.
Yes. Do you have any other query up to now?
No. Thank you.
Okay. So does anyone has other query to ask? You can ask now, otherwise I will proceed. Or in any time, you free to stop me anytime and ask your query. I will try to answer that, whatever query you have. Okay, so let us move to sodium lamp. So some of you must have done this experiment, or some of you may not. Uh, in Newton's ring experiment, we use sodium lamp, and we assume that the wavelength is monochromatic, and we take the wavelength is 589.3 nanometer. But in reality, the sodium lamp, it actually consists of two closely spaced lines, which we denoted as D1 and D2 line. So D1 line is that line which is wavelength around 5890 angstrom, and D2 is line wavelength around 5896 angstrom. So if you see figure 3, we see that the separation between this, the separation or the line width between this D1, D2 lines is 6 angstrom. So in reality, in actual practice, we can represent the wavelength of this sodium lamp by this expression 589.3 plus or minus 0.3 nanometer. And if we further reserve this figure 3, we notice that this D1, D2 lines also have some finite spreading, which is much less, and it is less than 0.1 angstrom. So this is all about the sources that is other than laser source. Now, if you see a laser, so the line width of a laser is much smaller than the sources that I have talked till now. So for laser, the line width it falls around few nanometer to 10 to the minus 6 nanometer. If you express this 10 to the minus 6 nanometer in terms of angstrom, you can see it is 0.000001 angstrom. So you can, by this expression only, you can easily see how narrower this line width of the laser is. So that's why we say a laser is highly monochromatic. So to find out let's take an example. So we want to find out the line width of a laser source. So you must have known this expression, frequency equal to C by lambda. So if you take the derivative, delta nu will be equal to minus C by lambda square delta lambda. So for line width, it is delta lambda. So delta, if you rearrange this expression, you can get delta lambda is minus lambda square by C delta nu. So if you know what is lambda, what is C, and what is delta nu for your source, you can easily find out what is the line width of your source you are talking about. So let's take an example. So if you consider lambda is 1 micrometer and delta nu is 1 Hz, you can easily see the line width will comes around 10 to a minus 20 order, minus 20 meter order. So here only you can see how narrower this line width is. So this means that the laser source we will see is highly monochromatic source. So this is all about the one of the special properties of the laser, which is highly monochromatic nature of this laser. Now let us move to our what is the components of a laser. So the components of a laser, it is similar to the components that we found in an electronic oscillator. So if we, as Sir said, electronic oscillator, it's a source of radio frequency. Similarly, laser is also a source of electromagnetic radiation in the optical domain. So if we compare the components of a laser and a electronic oscillator, we see that they share some fundamental similarity. Like in electronic oscillator, we have three components. One is power supply, other one is active device, and other one is feedback circuit. So using these three components, we can produce a stable and continuous output of this radio frequency out of this electronic oscillator. Similarly, in laser, what we have? We have pump, active medium, and a optical resonator. And using these three components, we can produce a stable and amplified output of a incoming source. So this is the comparison between an electronic oscillator and a laser. Now we will see how does what will happen when this pump interact with the active medium. Okay, so let us move the interaction section. So if you see, the radiation is nothing but a pump in the component, and a matter is nothing but a active medium that we use for amplification purpose. So now we'll see the interaction between this pump and active medium. So I think till now nobody has any query. If you have any query, feel free to stop me anytime and ask your query. I think all are unmuted, so you can ask your query. Okay. Otherwise, you can also write in the chat section there. After, if you have any query, then I will try to answer that. So, radiation, you know, it is a electromagnetic wave where where the quantum of energy is quantified by photon. So each photon has energy of h nu. This expression, I think all you know. H is the Planck constant and nu is the frequency. So the value for the Planck constant I have written down here if anybody needs. So radiation is electromagnetic wave, and if you see matter, so matter is nothing but a collection of atom where the electrons revolves around the nucleus in certain quantized energy levels. So now when this radiation, when it interact with the matter, what will happen is either one of this procedure will happen. One is absorption, another one is emission. So emission we'll see later. The emission can be it can be of two types. One is spontaneous emission, other one is stimulated emission. So spontaneous emission means it do not require any radiation, any external condition for this emission. And for stimulated emission, what we need a external source for this emission to happen. So that's why we have classified it as a spontaneous emission and stimulated emission. And Before going into the details of this absorption process, emission process, let's see some of the quantum mechanical concept that will help us to explain this phenomena of absorption and emission. So the first is Planck's law of radiation. So it basically tells us about the thermal radiation from a black body. So if we have a source and we want to find out what is the spectral energy density of this source, then we can use Planck's law of radiation. So spectral energy density is nothing but energy per unit volume between frequency nu and nu plus d nu. So according to Planck's law of radiation, you can express this spectral energy density as U nu d nu equal to 8 pi h nu q divided by CQ and 1 divided by a exponential factor which is e to power h nu by kBt and d nu. So equation 2 is the expression for Planck's law of radiation for a for to find out the spectral energy density. So if you from this expression, if you want to find out what is the total energy density, what you have to do, you have to take the integration. So if you take the integration, you can find out what is the total energy density for unit volume. Now, if you see equation 2, you can write it further as if you take out a factor of h nu in equation 2a, so we will see you can write the spectral energy density in terms of three factors. The first is the density of state, second one is the occupation probability, and the third one is the photon energy. So the density of states, which is rho nu d nu here, so it basically tells us about the number of states that is available between volume for unit volume between frequency nu and nu plus d nu. So it tells us about the number of states per unit volume. Now we have certain number of states that is available for us. The second expression is what is the probability of getting that state. So it is expressed by the occupation probability, which is 1 by e to power h nu by kBt minus 1. So the occupation probability will, by multiplying these two parameters, like the density of states and the occupation probability, we'll find out what is the actual number of states that is getting occupied uh, in a spectrum. Okay, and h nu is the photon energy, which you all know, I think. Mamta, do you have any query? Or okay,
Yes.
I saw you raise your hand, so I thought that you have any query. So it's okay.
Yes.
Now I think. Okay. So this is all about the Planck's law of radiation for a source and to find out the spectral energy density. So Mamta, you can ask your query.
ये फॉर्मूला में 8 पाई एच न्यू क्यूब बाय सी क्यूब जो है वो डेंसिटी ऑफ स्टेट्स है, नंबर ऑफ स्टेट्स पर यूनिट वॉल्यूम, मतलब कौन सा स्टेट में समझ नहीं कुछ, नंबर ऑफ स्टेट्स पर यूनिट वॉल्यूम न्यू और न्यू प्लस डेल यू के बीच में.
Yes. Like in a spectrum, we have different energy level. Like it's not like every energy level is filled. It's like only certain levels are filled and certain levels are unoccupied. So density of state will it will tell about what is the number of state per unit volume in that spectrum.
Okay,
So number of state that is available in that volume.
energy level.
Yes, in an energy level, it will tell about number of states for unit volume in that frequency range, nu and nu plus d nu.
Okay, and
The
what
occupation, it will tell about what is the probability of occupying those in those states. A probability.
Probability of finding any state.
Energy. In between nu and nu plus T nu.
Okay. Okay.
And H nu is the photon energy.
Yes. And what is the rho function of nu, del nu, del nu?
It's like rho nu is 1 minute. So rho nu is a function of frequency, right? It is 8 pi nu square by CQ. So the density of state, it will vary according to the frequency. That's why we write rho nu. Rho is a function of nu. It's 8 pi nu square by CQ.
Okay. Yes. Yes.
Okay. So now let us move to the atomic population. So atomic population, it will tell us about. Mamta, if you don't have any query, then can you please unraise your hand? Okay. So atomic population, it basically tells about how the so in an atomic system we have quantized energy levels. So atomic population, it will tell us about how these quantized energy levels are occupied by atoms. So if you see this figure, so this is the schematic of a atomic energy label, which is quantized energy label E1, E2, E3, and E4. In this quantized energy level, you will see some of the atom will occupy E1 state, some of the atom will occupy E2 state, some will occupy E3, and some will occupy E4 state. So now to find out how these atoms are distributed across this quantized energy level. So what we use, we use Boltzmann statistics. So we use these statistics to find out what is the distribution of atoms around the discretized quantized energy levels of a atomic energy level. So according to, if you see equation 2b, it is telling about the probability of occupying a state. So according to Boltzmann statistics, you will see the probability that one. So let me tell you clearly. So P of E is nothing but probability that the energy level EI is occupied. So EI can be anything, E1, E2, E3, E4, and this probability is equal to GI multiplied a exponential factor, which is e to power minus EI by KBT. So the first term here is degeneracy factor, which basically tells about the degeneracy of a level. So if let's say we have two energy level, and one of this energy level have two degeneracy, this means the energy level is double degenerate. So for that case, we have GI equal to 2. So GI equal to 2 means two energy level have same energy. So this is what we mean by degeneracy factor. And the second factor is e to power minus EI by KBT. EI is the energy level, E1, E2, E3, E4, and KBT is the KB is the Boltzmann constant, and T is the temperature. So in our course, we'll take GI as a one. That is, we will treat the system as non-degenerate system. So for that case, we can write down P of EI is equal to e to power minus EI by KBT. So this is the expression for the probability how these energy levels are occupied by atoms. So let's understand this by taking the example. Let's say I have again plotted this energy level in this diagram. So this is the atomic energy level E1, E2, E3, and E4. So and N1 is the number of atoms for unit volume in energy level E1. N2 is the number of atoms for a unit volume in energy level E2. N3 is the number of atoms for unit volume in E3, and N4 is the number of atoms for unit volume in E4 level. So according to this equation, you can write what is the number of atoms that occupy the E1 level is N0 e to power minus E1 by kBT. So, okay. So Dipti, degeneracy means, 1 minute. So degeneracy means two different energy levels have same energy. So if you see hydrogen atom, all of you must have known hydrogen atom. Hydrogen atom, let's take me draw the diagram. For hydrogen atom, the energy level is written as minus 13.6 divided by n square, right? So the energy, it depends on this quantum number n. So depending on the quantum number, we have different energy level in the hydrogen atom. Now, it's not like we have one quantum number which specify energy level. To specify energy level, we use different types of quantum number. One is principal quantum number, which is n. Another one is azimuthal quantum number. Another one is spin quantum number. So if you see, for if you ignore Ls, so we tell that this n equal to 1 state is a non-degenerate state. But if we consider Ls, then we will see that these levels can be further split into 2 or 3 parts according to the interaction between Ls. So if this energy level, if you consider the interaction between Ls, if it is getting split into these two levels, then we say that this state is double degenerate. I think it is clear to you what is degeneracy means. So the term means these levels have same energy. So 2 means 2 energy levels have same energy. 3 means 3 energy levels have same energy. So in absence of this Ls interaction, what we'll see, these two levels have same energy, right? If you don't, so let me explain it again. So in hydrogen atom, we have En equal to minus 13.6 divided by n squared. So in absence of Ls interaction, we say that this level E1 has energy minus 13.6, E2 has energy minus 3.4. So if you, this is all based on the quantum number n. So if you now consider the two other quantum number Ls, then we see that this energy level can be further split into 2 or 3 parts, depending on the Ls interaction. So this means that in absence of Ls interaction, these energy levels have, actually this energy level is not single, it is two energy level that is same energy in absence of Ls interaction. So this means that this energy level is double degenerate, it has degeneracy factor of 2. Similarly, if this level has 3 energy level that is same energy, we will say Gi equal to 3. So this is what we mean by degeneracy factor. So Dipti, it is clear to you? Is it clear to you? Okay.
Yes, ma'am.
Okay, so let me move. So we're calculating what is the atomic population of E1 level. So atomic population of E1 level, you can express as N1 E1 equal to N0 e to power minus E1 by kBT. Similarly, the number density, that is number of atoms per unit volume, which is N2. In E2 level, you can write it as N0 E2 bar minus E2 by kBT. Now, if you take the ratio of this two number density N1 by N2, what you will get is E2 bar E2 minus E1 by kBT. So this is how you can calculate the atomic population, the relative atomic population of energy level 1 with respect to energy level 2. So now if you see one example, if you take, let's say E2 minus E1 is 1 electron volt, and kBT, if you take room temperature, so kBT is, if you find out what is the kBT value, if you take kB, the value of kB is 1.38 into 10 to the minus 23 joule per Kelvin, and T you can take it as 300 Kelvin. So if you put this, then you will get that the kBT is for room temperature, it is 0.025 electron volt. Now, if you put this in this expression, you will get that the N1 by N2 ratio will become e to the power 40, which is nothing but 0.03 into 10 to the power 18. So here you can see how large this number is. So this tells that at room temperature, that is at T equal to 300 Kelvin, the atomic population of energy level E1 is much greater than the atomic population of E2. So this means that at thermal equilibrium, most of this atom will try to occupy the lower energy state, then they will start filling the higher energy state. So the atomic population of ground state will be greater than the atomic population of the higher energy state. So this is about the atomic population, how these atoms are populated across the discretized energy level. So now we'll see the interaction. So before interaction, let us see the population diagram. Mamta, you can ask your query.
The excitation here is of electrons or atoms.
Yes, atoms. Like some atoms occupy the lower energy level, higher energy level. It's like atomic population.
But atoms are in like a solid state, right? We have studied the
By
exact excitation of electrons in each atom.
excitation of atoms across, okay,
Sorry,
it is about, by atom we means electron excitation.
right?
1 minute. So can you please ask your query again? I'm confused a little bit. Can you please repeat your question?
Yes. I'm asking that this excitation, E1, E2, the energy levels, like there's excitation of atoms from energy levels E1 to E2, E2 to E3, or excitation of electrons from
So
E1 to E3.
it is excitation of electron, which is uh,
I think
inside
it's
the
excitation of electrons.
atom. Yes, it means excitation of electrons. So let me show you the slide.
Yes.
1 minute. So this slide will be uploaded in the portal. I think it is not uploaded till now. So it will get.
Yes, it was their excitation of atomic system.
Yes,
Previous
it's like number of atoms per unit volume state. So by atomic excitation, we mean the electron excitation inside the atom. Like in some atom, the electron will get excited to E2 level. In some atom, it will excited to E1 level. Sorry, E3 level. So I think here the atomic excitation means we are in quantum regime, we are looking at the electron excitation inside this atom. Yeah, I think you are correct.
Okay. Thank you.
So let us here. So now if we look at the population diagram, so we found out that the N of EI is directly proportional to E to power minus EI by EBT, right? So if we plot this expression, then what we'll get, we'll get a graph like this. So we'll see a exponential decay of this number density across the different energy level. So as we increase the energy level, the number density will gradually decrease exponentially. So if you see in first figure, so here E1, E2, E3, E4 as the energy level, the quantized energy level that I have shown here in this figure, and N1, N2, N3 are the corresponding population density. Like N1 is the population density of E1, N2 is the population density of E2, similarly N3 and N4. In this diagram, if you see the population density of N1 is greater than N2, N2 is greater than N3, and N4 is greater than N3 is greater than N4. So we can tell at thermal equilibrium, the population dense, the most of these atom will try to occupy the ground state instead of the higher energy state, right? Thermal equilibrium. Now for we'll see, Mamta, do you have any query? You have raised. Okay. So in for laser action to happen, what we need a population inversion that we'll see in our upcoming section. So by population inversion, we mean at thermal equilibrium, we have N1 is greater than N2. Now, by population inversion, we mean N2, the energy number density of higher energy level is greater than number density of the lower energy level. So this is what we mean by population inversion, which is required for amplification in laser. So if for this, if you look at this figure, figure 2, so here you can see the number density of N1. It is lesser than N2. So when we can achieve this condition, we can achieve this condition by using an external switchable pump. So by pump we mean an external radiation that we use to excite the active medium. So by using an external pump, we can achieve this population inversion, and we also can achieve amplification of light using laser. Okay, so this is all about the quantum mechanical concept that will help us to understand the interaction process that will happen when a pump interact with the atomic system or active medium. So now let us move the interaction picture. So previously we see that the interaction will be of two types. One is absorption, another one is emission, right? So absorption and emission. The emission is of two types. One is spontaneous emission, and another one is stimulated emission. So let us see the absorption spectrum first. So let's say we have a input source, which is a spectrum like this. So it's a broadband source. So now if we excite one atomic system using this input source, then we want to find out what will happen in the output when we pass through the pass this broadband source to any atomic system. So we see that the atomic system are these are characterized by quantized energy level, where the electron occupies discrete energy levels. So when this broadband source, when it interacts with the atomic system, it will excite the ground state electron to the higher energy state. So it's so when so it's not like every frequency will excite this atom to the higher energy state. So whenever to excite, let's say we want to excite this atom to the E1 level. So this means that the frequency of this incoming source must be equal to E2 minus E1 by H. So if the incoming source has frequency this, then it will excite the ground state electron to the E1 level. Similarly, if you want to excite one electron from, let's say, E0 level to E2 level, right? So it means that the frequency of this incoming source should be equal to E2 minus E0 by H. So whenever, if all these frequency are present in this broadband source, what we will see, we'll see that the electron will get excited to the E1 level or E2 level or E3 level. So in the output, if you see the output now, in the output, what we'll see dips. So, and the dip is not like a continuous dip, like in every frequency we'll see a dip. It's like only at a specific frequency we'll see a dip in the transmission spectrum. So these dips, they correspond to the different type of transition that is happening in the atomic system here. It may be the transition from E0 to E1 or E0 to E2 or E0 to E3. So depending on the transition, we'll see discrete peak in the transmission spectrum. So this means that the dips correspond to the different transition between the quantized energy level in the presence of this broadband source. So this result, this also confirms that the energy level of an atomic system is quantized. So it only absorbs at a specific frequency, not at all frequency. So this is all about the absorption spectrum. Now we'll move to the emission spectra. So similar to the absorption spectra, if you now incident one source which is frequency nu to a atomic system. So now we want to see what will happen in the emission spectra of this atomic system. So similarly, we see, 1 minute. Quantized, it means they are discrete. They have different energy levels. It's not like continuous. Like let's say you have a spectrum. You must have known semiconductor, right? Like say in semiconductor we represent bands like conduction band and valence band. So it is continuous energy level. But in atomic system, what we have is discrete energy level. Only some energy level are occupied and like this, discrete. So here we see there is energy level around this, but there are no energy level in between this two energy level. So these are discrete energy level. So is it clear to you, Mamta?
Yes.
Okay. So let us move to the next part. So now we are studying the emission spectra through a atomic system. So now using this, let's say the whatever energy of this incoming source, it is equal to E2, E4 minus E2. Sorry, E4 minus E1, not E2. This is E1. So this means that the frequency will be E4 minus E1 by H. So this indicates that the frequency, the incoming source will excite the system from ground state to the fourth state, E4 state. Now, instead of absorption spectrum, we are studying the emission spectra. Like what is the uh, spectrum of this atomic system after getting absorbed, after it absorbs a incoming radiation of H nu. So, if these energy levels are discrete, we will see that if the atom is getting excited to E4 level, then during de-excitation, when it makes a downward transition, it may comes like this. Like it may make a direct transition from E4 level to E1 level, like direct transition. Or it may take a path where it come down to E2 level, then from E2 level it come down to E1 level. Or it may happen it will come down from E4 to E3, E3 to E2 or E2 to E1. So it can take various paths during the transition process, and it's not like all these transitions are allowed. There is selection rule that we'll study later. So only some transitions are allowed during this downward transition. So because of this different path, what we'll see peaks in the transmission spectra. So if you see the right figure, we'll see a peak here, and peak here. So these peaks, they correspond to the different downward transition between the discretized energy levels. So as I said, this distinct peak correspond to different downward transition, and it also confirms that the atomic energy levels are quantized. So now if we take, let's take one example of hydrogen atom. So in hydrogen atom, we have in the emission spectrum, we have several spectral series. So we have series like Lyman series, Balmer series, Paschen series, Brackett series, and Pfund series. So these are the different kind of series that we see in the emission spectrum of hydrogen. So if you see in details, let's see Lyman and Balmer series. So Lyman series, it corresponds to this downward transition which happens from higher energy level to n equal to 1 level. So, so let me give a brief of hydrogen. So as I said, the hydrogen atom energy level is given by minus 13.6 divided by n square. So it is the energy levels are denoted by the principal quantum number n. So in this system, we have n equal to 1 level, n equal to 2 level, n equal to 3 level, n equal to 4 level. So we have this energy levels, or it's not like the separation between them is constant. So we'll see it is varying as the energy is varying as n square. So this means that the separation will decrease as we move to higher energy level. So this separation are not constant. So in this energy level, if a transition, a downward transition is occurring from higher energy level to n equal to 1 level. So this corresponds to the Lyman series. So here you can see this transition. It is from n equal to 2 to n equal to 1 level. And the second transition from n equal to 3 to n equal to 1 level. Similarly, n equal to 4 to n1 level and n5 to n1 level. So if the transition, downward transition is occurring to n equal to 1 level, then we say it is Lyman series. Similarly, Balmer series is for those downward transition where the transition is happening from higher energy state to n equal to 2 state. Okay, this is for Balmer series. Let's say we have we have transition from n equal to 3 to n equal to 2 level, or n equal to 4 to n equal to 2 level. So this all transition will fall in the Balmer series. So these are the two series, and other series like Paschen series is for all downward transition from higher energy level to n equal to 3 level, and bracket series is for uh, higher energy level to n equal to 4 level, and Pfund is for higher energy level to equal to 5, n equal to 5 level. So depending on the transition to different discretized energy level, we have different spectral series for hydrogen atom. Okay, so this is all about the emission spectra of hydrogen atom. So let me ask you, till now, does anyone has any query in any part of this note? If you have query, then you can ask. Feel free to ask. Otherwise, I will move to the next section where we will study the rate of this absorption and emission process. Okay, seems like no one has any query. So let us move to the rate equation. So as I said, the interaction between the radiation and matter will lead to absorption and emission. So emission will be maybe spontaneous emission. Okay, numerical, I don't think I would be able to do in this section because it's already half an hour is there. From the next section onwards, I will cover both the concept that is taught in the class as well as the numericals, as well as the assignment or the doubts regarding the assignment, as well as I will solve, if time permits, then I will solve additional problems also, so that it will be helpful for you to get some idea about other question, and you can solve the assignment easily also. So in this section, uh, um, we are not going to cover the numerical part. From the next section onwards, I will solve the numerical as well as I will teach the concept also. So it is a 2-hour section, right? So that's why we have limited time. So don't worry, I will try to cover in the next section. So let us move to the rate equation now. So as I said, the emission is either spontaneous emission or it may be stimulated emission. Let us see the absorption process first. So we are treating now we are treating a atomic system which have two energy level. So two level system. So this means that the energy level is E1 here, the energy is E2 here, and the number densities for E1 level is N1 and N2. And we are interacting a source of frequency nu and spectral density u. So in the previous section, previous part, we see that the whenever this radiation interacts with this energy, discretized energy level, absorption will happen or emission will happen. So this rate of absorption, which is defined as number of absorption per unit time per unit volume. So this rate of absorption, it is directly proportional to N1, that is the number density of the E1 level. And also it is directly proportional to the spectral energy density of the incoming source, you know. So absorption depends on two factors. One is the atomic population of the N1 level, E1 level, and the spectral energy density. So this means that we can write the rate equation for absorption is equation 1, which is B12 N1 you know. B12 is a proportionality constant. Later we'll see that it is a Einstein constant for absorption process. This is about the rate of absorption. And for emission, we have, yes, Mamta, ask your query.
क्या एब्जॉर्प्शन किसका एब्जॉर्प्शन है मतलब लाइट
So whenever, it's like the incoming light will get absorbed by this atomic system. So the atomic system will get excited to higher energy level. It's the energy absorption of the incoming light. So previously I told you whenever this nu equal to E2 minus E1 by H, then this will excite the atomic system from E1 to E2. So for excitation, it requires energy, right? This E1 level has certain energy, this E2 level has energy that is higher than E1 level. So to get excited to this E2 level, this the lower atom, they will require energy. So that energy will come from the incoming radiation, which is H nu.
ओके तो एब्जॉर्प्शन इज ऑफ एनर्जी एनर्जी का एब्जॉर्प्शन और एमिशन भी एनर्जी का
Yes. So whenever
Yes.
this transition will happen, so let's say you have higher energy level and you are coming to lower energy level. So this means that to go to the lower energy level, you have to release your energy. So this energy will release in terms of photon. Photon or some other kind of radiation is there. Phonon is also there. But for now, we'll consider photon emission.
Yes.
So this is okay. Rate of absorption. It depends on N1, you know, B12. And for emission, when the transition will occur from higher state to the lower state, let's say we are dealing with spontaneous emission. So the spontaneous emission do not require the presence of this external light source. So this means that the spontaneous emission only depends on the atomic population of the E2 level, the level from which the transition is occurring. So for us, it is occurring from E2 level. The transition is occurring from E2 to E1 level. So that's why the rate of spontaneous emission is directly proportional to N2. So if you then we can write the rate of spontaneous emission is A21 N2. Okay, A21 is the proportionality constant. And for the next emission, which is stimulated emission. So for stimulated emission, what we'll see, the stimulated emission requires the presence of this external light during the transition. So that's why the stimulated emission is directly proportional. It depends on the atomic population of the excited state, as well as it depends on the spectral energy density of the source. So that's why the rate of stimulated emission we can express as B21 N2 you know. Okay. So B21 means 2 to 1 transition. Similarly, B12 means 1 to 2 transition. A21 means 2 to 1 transition. And B, the constant B we used for stimulated process, like stimulated absorption or stimulated emission. and A is used for spontaneous case, where like we have used for spontaneous emission. So these are the rate equation. Now, if we consider a equilibrium condition, so let's say the system is at equilibrium. So that means the number of upward transition will be equal to number of downward transition. So upward transition means absorption process, downward transition means we are dealing with emission process. So now we can all we have to do is equate the rate equation for absorption process and emission process. So absorption process we see it is equal to B12 N1 and for emission process it contains two parts. One is spontaneous emission and another one is stimulated emission. The first term here is the rate equation for spontaneous emission, which is A21N2, and the second this is for stimulated emission. Now, if you rearrange this equation, you will get is in terms of this expression. U equal to A21N2 divided by B12N1 B minus B21N2. So in the next equation, what I have done, I have divided N2 in both numerator and denominator, and I have also divided B21 in both numerator and denominator. So if you do this, you will get expression like this. So you can express as A21 divided by B21 divided by whole divided by B12 by B21 N1 by N2 minus 1. So this is what we got after equating the upward transition and downward transition. Now earlier we have studied about the atomic population. So for a non-degenerate system, you can write N1 as N0 e to power minus E1 by kBt and N2 as N0 e to power minus E2 by kBt. So if you take the ratio N1 by N2, we'll use it in this expression. So if you take the ratio, you will get e to power E2 minus E1 by kBt. And E2 minus E1 is nothing but H nu, right? So the N1 by N2 is equal to e to power H nu by kBt. So now putting N1, we'll put N1 by N2 in this equation. The final expression will get is equation 5. So this is for a non-degenerate atomic system, the spectral energy density expression. And earlier we have also studied the spectral energy density using the Planck's laws of radiation. So if you now, according to this Planck's law, we see that the spectral energy density can also be expressed as equation 6, 8 pi h nu q by cq 1 by e to power h nu by kBt minus 1. So what we have to do? We have to equate equation 6 and equation 5. So if we equate equation 6 and 5, what we'll get is that there is no B12 and B21 factor here, but there is a B12 divided by B21 factor here. So this means that these B12 and B21 are equal, so that we can get a factor of 1 in both the cases. So by equating, we'll get B12 equal to B21, and we'll get a equation like this: A21 by B21 equal to 8 pi h nu q by c. So these two relation, these are Einstein relation, and these are given by Einstein. And this Aij and Bij, these are Einstein coefficient. So Aij, we use it for spontaneous emission process, and Bij, we use it for stimulated transition process like absorption process and stimulated emission process. So now if we, let's take instead of indexing this constant, if you take A21 is A and B12 and B21 is B, so now we'll calculate what is the uh, rate of spontaneous emission with respect to the rate of stimulated emission. So we'll see which emission dominates at the room temperature. So this is like we want to find out R, which is nothing but rate of spontaneous emission with respect to rate of stimulated emission. So this is rate of spontaneous emission is given by A into, and rate of stimulated emission is given by B N2 N2. So if you can see there is a common factor N2 here, so N2 N2 will cancel. So what we left with is A by B N2. So what you have to do now is to take this equation to Einstein relation and put it in this expression. A by B is nothing but 8 by h nu q by ck. And you already know it is given by equation 6, 8 by h nu q divided by cq, 1 by e to power h nu by kbt. So if you put A by B expression and u nu expression, you will get this final expression, that is R equal to e to power h nu by kbt minus 1. So this is the final expression. Now to quantitatively find out which emission process dominate, so let's take some values. So if you take h nu 1 electron volt and kbt is the room temperature, which is 0.025 electron volt. If you now put this in this expression, what we will get is R is e to power 40 minus 1. So here only you can see the rate, the R value of R is much large. So that means the R is nothing but the ratio of rate of spontaneous emission with respect to stimulated emission. So this is the ratio of spontaneous emission with respect to stimulated emission. And we are seeing at room temperature, it is a larger value. So this means that at room temperature, the number of spontaneous emission, it dominates over the number of stimulated emission. So we'll not see, will not get any amplification process in the room temperature. Okay. So this is all about the rate of absorption as well as the rate of emission that will happen when the radiation will interact with the atomic system. So till now, does anyone have any query?
Ma'am, can you move to the previous slide?
Okay. This one?
Yes, just I want to doubt all.
Sorry, could you please
Yes, ma'am.
repeat your question?
No, I have not any question. I want to just revise that if I'm in doubt or not.
Okay, okay. So these equation, these are all there in the week 1 PDF file. So if you see, this PDF file will get available soon. So if you see these all are there in this PDF file. This one.
Yes, done, ma'am.
Okay, okay. So let us move to our final concept. So this is about the lifetime of spontaneous emission. So it's a measurable quantity. That's why we want to study this. So if we calculate the spontaneous emission lifetime, then we can easily we will see this spontaneous lifetime is related to A here. So if we know A, then we can easily calculate what is the value of B by using this expression. So that's why we are next going to study what is the lifetime of spontaneous emission. So as we have seen earlier, so the rate of spontaneous emission, it is given by A and 2. So A is Einstein coefficient, N2 is the atomic population of E2 level. So now this rate you can write it as dN2 by dt, which is equal to minus of AN2. So we are taking minus because with respect to time, the population of this N2, the value of this N2 will decrease because of this spontaneous emission process. So that's why we have write it as the rate we write it as minus of dN2 by dt equal to AN2. So we have taken a negative because the N2 value will decrease over time because of spontaneous emission. So now if we rearrange this equation, so you take N2 to left side and dt to right side. So we'll get dN2 by N2 equal to minus of A dt. So if you integrate this equation, what the general solution is ln N2 equal to minus of AT plus C. So this is the general expression. So now if we consider a case where at time t equal to 0, we have N2 T0 equal to N2 0. That is the level 2 is occupied by N2. At t equal to 0, we have N2 0 population in the E2 level. So if you put this in this equation, then what we'll get? We'll get the value of this constant C. So we'll get C equal to ln N2 0. So we calculated what is the value of C. Now for the other extreme, like at t equal to t, let's take N2 t equal to N2 t. Now we'll put this again in this equation. So if you put it, what you will get is ln N2 t equal to minus of AT ln N2 0. So this is the C factor and this is minus AT and this is ln N2 t. So now what I have done is I have rearranged the equation. I have taken ln N2 0 to this side. So you will get ln N2 t by N2 0 is minus of AT. So in final, we will see the final expression is N2 t equal to N2 0 e to r minus of AT. So this is the final expression. This tells us how the number density of this E2 level will change with respect to time. So if you plot this equation, we'll get a graph like this. So this is a plot between N2t with respect to time. So we are saying it is N2t is directly proportional to power minus of AT. So that means it will decrease, it will decay exponentially with respect to time. So this blue plot is the exponential decay of this N2 population, this N2 with respect to time. Now if if you see this exponential factor, it is minus of exponential factor is minus of 80. Now, if you take one condition, let's say we have time t which is equal to 1 by a. So we are measuring the number density at time t equal to 1 by a. So if you put t equal to 1 by a, what will get? N2t equal to N20 e to power minus 1, right? So this means it is N20 by e. So this indicates that after this time, the population of this N2 level will decrease to 1 by e of its initial value N20. And this time, this 1 by e time is what we define as the lifetime of this spontaneous emission process. So lifetime for this spontaneous emission we define is the time at which the atomic population decreased to 1 by e of its initial population density. So initially we in level 2 we have N20. After time t equal to 1 by a, this N2T0 will become N20 divided by a. So this is known as the lifetime of spontaneous emission, which is indicated in this plot. Now, this spontaneous emission lifetime, we can measure it during the experiment. So how we can measure it? Okay, Mamta, you have any query?
Yes. How do we know that at time t is equals to 1 by a only the spontaneous emission lifetime will be 1 by e times n2, not
1 by e times. So spontaneous,
e times n2.
your voice is breaking. Could you please repeat?
Yes. How we come to know that at time t is equals to 1 by a, the population density will be 1 by e times the original not n2 not.
If you, it's like it, I think it, if you get it from this rate equation. So if you see this equation which we have calculated, the rate equation of this N2 level. So if you see N2T is nothing but N20 e to power minus 80, right? This equation. I'm talking about this equation. So if you put here, if you
Yes,
put
is equals to 1 by a, right? If we put,
then
then we will come to know that n number yeah, population density is 1 by e times the original one. But how
yes.
do we know that we have to put t time is equals to 1 by a to get the
So you mean to
population
ask?
density 1 by
So you mean to ask why we are considering 1 by a time only for lifetime, right? Not other value.
yes, ma'am. Yes, ma'am.
So I think it's like it's similar to the way we are defining the line.
Sorry,
1 minute.
designing
1 minute. 1 minute. Okay. Okay. Mamta, the answer, I think someone has asked this same query in the forum and it's already answered. Just now the NPTEL team has addressed this question. So you can get back to the forum and find out the answer there. Otherwise, one hint I can tell you is similar to the line width. Like for line width, we have considered the 50%, like the full width at half maximum, and other one we are ignoring. So it's like a definition. So like below 50%, the contribution is negligible for line width. Similarly, here for lifetime, we are considering 1 by A. Like below that. Uh, so let me get back to you with the proper answer. I think it's more related to the way I am telling it is mathematical only. So you want a, I think, more uh, uh, answer that is related to concept. So let me get back to you in our next section. Otherwise, you can revisit the forum also. So according to me, it's like a definition that we use to uh, define the lifetime of a process. So below 1 by E, the process doesn't happen. Means it happens, but the contribution is less. But above 1 by E, the emission is still happening. Like that only. But let me get back to you with a proper answer in our next section.
Yes, ma'am. Thank you.
Okay. So let us see how we can measure the spontaneous emission lifetime in the experiment. So here is this is one of the schematic of a experimental process where we can measure the spontaneous emission of a atomic system. So if you see, this is a light source. So the light source is initially it is passed through a mechanical chopper. So chopper is nothing but it consists of two regions. One which is covered and another one is which is not covered. So it consists of two alternative region of covering and uncovering. So it has blades and non-bladed region. So what will happen when the light will pass through this open region? So it will easily pass through this chopper and excite this atomic system. But whenever the light will fall in this cover region, so the light will be completely blocked by this chopper and it won't be able to excite the atomic system. So this is the chopper that is used to get a pulsed output like this. So if you see this figure, this is the output that will get in this position. So in this position, we'll get a pulsed output because of the mechanical chopper. Some light will pass and some light will, in one instant, the light will get passed through the chopper. In another instant, in the next instant, it will be blocked because of the presence of this blade region in this chopper. Now, this input is fed through a atomic system and output of this atomic system is fed through a photodetector, which where electric current will be generated, and we'll see a plot between potential versus time in this cathode ray oscilloscope. So now let us understand what will happen. So let's see the light is passing through this open region. So light is, so initially the light is passing through this open region where there is no blade. So this means that the light will pass through the chopper and it will excite the atomic system. So when this excitation will happen, that means the number, the N2, which is the population density of E2 level, it will increase. And simultaneously, because of this increase in number density of N2 level, we'll see that as the emission process is directly proportional to N2. So we'll see that the spontaneous emission process will increase. So according to that, the P output here it will also increase when the light pass through a non-bladed region, like the open region. And so when this when this spontaneous emission will increase, what will happen? The current through this photodetector, it will also increase. And according to that, what we'll see in the output is that an increase in the voltage. So it will increase up to the time where the light is passing through a non-bladed region. Now, when now the chopper is rotating, so now it will incident a region where we have blade. So that means the light will get blocked by it, and no atomic excitation will occur. So the N2 level, the N2 value will decrease, and similarly the spontaneous emission will decrease, and the P output here is also decrease. So due to the decrease in P output, we'll see a gradual decay in the voltage in the output of this cathode ray oscilloscope. Now again, as the chopper is rotating, we'll see the light will again also pass through this non-covered region and non-bladed region. So it will again excite the atomic system. Again, we'll see spontaneous emission, and again we'll see increase in the voltage. So we'll see a output like this. We'll see increase in voltage, then decrease, increase in voltage, then decrease, increase in voltage, then decrease. From this voltage plot, we can calculate what is the spontaneous emission lifetime. So as the voltage is directly proportional to, if you see the VT, the voltage through, let me take one different color. So the voltage, it is directly proportional to the current through the photodetector, and it is directly proportional to P output, and it is directly proportional to N2. So N2, you know, N2 is nothing but N2 0 e to power minus T by TSP. So to find out the TSP, what we have to do? We have to H voltage BT is directly related to N2. So this means that for to get the TSP time, what we have done, we have considered a case where the population density of N2 decreases to 1 by E of its initial value. Similarly, as VT and N2 are related, we'll see to find out the TSP, we'll take the time at which VT is decreasing to 1 by E of its initial value. So this way we can find out the spontaneous emission lifetime from this experiment. So VT you already know, this is VT, V0, and the time at which it decreased down to V0 by E is the spontaneous emission lifetime. So if you can in the experiment you can calculate the TSP, and from TSP, as you know, TSP is directly related to 1 by A. So from you can get the value of A then. So from A, you can easily calculate what is the value of B using this Einstein relation. So this is all about the concept that is studied, that were taught by Professor M.R. Sinha in week 1. So before ending the section, let me ask, do anyone has any query regarding whatever I taught till now? If you have any query, then feel free to ask. Otherwise, we'll end this section. From the next section onward, I will try to cover both the concept first and your doubts, as well as the doubts regarding your experiment, your assignment. if you have any query in the assignment. There is forum also, discussion forum. There you can also ask your doubts. If it's still not clear there, then you can ask me during this live section. And I will cover the concept as well as your doubts regarding the assignment. And if time permits, then I will do some additional problems also. So I think no one has any doubt. So let us end this section now. Thank you all for joining this section. So for the next session, we will again meet on next Saturday, same time, 4 to 6. And thank you all for joining this section. So let us meet in the next section. So goodbye all. Every Saturday, there will be live section which will be conducted by me. So it's more like a discussion where you can ask your doubts and your assignment doubt as well as the conceptual doubt. I will try to answer that. If I didn't have any answer during that time, I will try to reach you to in the next section to clarify your doubt. Every Saturday, 4 to 6, same time. Okay, so I think we can end this section now. So thank you all. Bye everyone.